Hello friends, in this session we will see voltage regulation by using zero power factor method, also known as ZPF method, which is also called as Portier triangle method. Let us begin. Okay, so before starting with this particular method, let us understand what are the different data which is required in order to solve the problems using ZPF method. Okay, so the test data required so that we can solve are the following. What are they? Number one, you will need the OC test data. What is OC test? Yes, come on. OC test is open circuit test. We have already studied it, correct? OC test as well as SC test. We had studied it in EMF method as well as MMF method. Is that correct? Yes, sir. So we will need OC test ka data. What does this OC test exactly give us? This particular test gives us the characteristic between what? Between open circuit voltage phase value on the y-axis versus field current. Is it correct? Yes, sir. This is what OC test gives us. Now, the second test data which we need is nothing but, yes, the second test data is nothing but short circuit test, SC test data. Is it right? Yes. So in this short circuit data, we will be getting what? We will be getting the short circuit current ISC. Correct or not? Yes. Which will be the rated current versus we need the graph IF, which is the field current. Is it correct? Yes, sir. Right. Now, also we need the third thing, which is resistance value, armature resistance value RA, which is what? Armature resistance value. Is it correct? Yes. Now, all this data we have already used where in EMF method, MMF method. Is it right? Yes. But now, apart from this, we need one more data. In this particular method, we need one more data. What is that data? Let us see. The new data that we need right now is ZPF test data. What is that? ZPF test data. What is this particular test? Let us understand how do we have this particular test, and then we'll see what will be the values which we'll get at the end of the results, and then how we will use them. What are the different steps in order to find the voltage regulation by using ZPF method? We will try to see that very soon. Okay, so now let us see what is a ZPF test exactly. Example, for example, you have got a stator, correct? Let us take the schematic diagram only. For example, this is your stator along with the bullseye, correct? Yes. For example, you are having let us say three phases. So this is conductor A, 120 degrees after that you will be getting conductor B, 120 degrees after that you will be getting conductor C. Now, if it is a two pole machine kind of like this, for example, this is the rotor on which field winding is there, correct? For example, this is north pole and this is south pole of the rotor, correct? Yes. Now, since if it is a two pole, then we know that A dash will be exactly 180 degrees opposite to A. So here we are going to get A dash. Similarly, here we are going to get B dash, which is exactly opposite to B and exactly diametrically opposite to C, 180 degrees. You will be getting what? You will be getting C dash. Is it correct? Yes, sir. No doubt till now. Now, what I'm trying to say is, what if I take out these terminals, kind of terminal A, whenever, because see, basically you will be, basically this particular rotor, you will rotate this by using a prime mover, correct or not? Yes. So for example, if it is rotating like this in anti-clockwise direction, it is rotating, speed is omega, example, then what will happen? EMF will be definitely induced in our stator conductors, correct? Yes sir, stator conductor EMF will be produced. Now what I will do is, let me take out these terminals A, B, just a minute, B terminal and C terminal, correct? Now what I will do now, and let me have these three also. What is this? C dash, C dash, B dash and A dash. So let us have these also. For example, these are taken like this, second one, and this C dash, they are taken like this, short circuited here, kind of. Okay, now example, now what are you supposed to do? You are supposed to connect a inductive load over here, purely inductive load. What are you supposed to do? You are supposed to connect a purely inductive load, so kind of like this, correct? Is it right? Yes sir, no problem, no worries, right? If you want, then your better understanding, let me make it like this. Is it right? Yes. Now, so basically you will be having a completely inductive load at the end, correct? Now this load has to be definitely what sir? Variable. So this load will be variable, correct? Yes. Now what will you be doing? What will you be doing? That is the thing, correct? What will you be doing? So exactly how this particular experiment is conducted in our laboratory, let us try to see that particular circuit as well, such that it will become a very easy understanding for you, correct? Yes. So let me have stator, armature, this is armature winding connected in star, for example. Now yes, this is the armature winding connected in star, correct? This is neutral point. Now you are having inductive load, correct? So let me have that inductive load over here, purely inductive load. This is inductive load, remember that, purely inductive load, correct? Yes. Now what I will do, for example, let me connect ammeter over here, let me have a switch like this. This is what, this is triple pole single throw switch, TPST switch, correct? Triple pole single throw switch, triple pole single throw switch, okay? Yes. Now what I will do is, this is your amperes, this is your ammeter, this is your ammeter. Now let me connect voltmeter also. So this is your voltmeter. See, here I will be having a field winding, this particular field winding which is there, let me have it here, correct? So this is going to be my field winding, correct? Let me connect ammeter here also, variable resistor, and that's it. Okay, so this is the machine slab structure, correct? Okay, no problem sir. Now just see what happens. At starting, when this field current, let me call this field current to be IF, let me call the current here to be armature current IA. Now for example, if you keep on at starting, if if is 0, if is 0, how much is the voltage? Voltage is also 0, no doubt, correct? Now as you keep on increasing this field current, as you keep on increasing the field current, how will you increase this? By wearing this particular rheostat, correct? Field resistance kind of, you are going to increase this field current. The moment you start increasing the field current, what will happen? What will happen? Your voltage will start increasing, voltage induced will start increasing. When your voltage reaches 85% of the rated, when your voltage reaches 85% of the rated, you are going to close this switch. You are going to close this switch, correct? Yes. Now once the switch is closed, what will happen? Definitely current IA will flow, correct? Yes. Now this IA current that flows, that current flowing through this, now see, you are going to flow rated current through this inductive load. Since it is flowing through inductive load, we will be calling that current to be IIL. IL stands for inductive load, IIL. And this is going to be what value? Rated value. Getting my point? Please tell me yes or no. Is it right? Yes sir. Now basically you will be getting here reading. What is that reading? That reading is going to be the field current reading. That is the first reading that you get. The second reading will be this voltage reading, and the third reading that you will get is IIL rated, correct? So basically you will get only one reading kind of for what field current, how much is this 85% of the voltage, and this IL rated, correct? Yes. Remember that this is a purely inductive load. That is the reason we call it as a zero power factor load. In such a cases, conceptually what happens is demagnetizing armature reaction happens, correct? We have seen that demagnetizing armature reaction effects happen, correct or not? Yes. No. So those all things have to be taken care of. Anyways, let us move on to the procedure, that what are we supposed to do. For this, what is the ZPF data that we have got? That is IF field current in amperes, correct? Then we got what? VIL. We got, definitely it was line value, we need to make it to phase value end of the day, correct? Yes. And then here it is what? IIL, which is how much? It is what? Amperes, line current, correct or not? Yes. Now all these values which are in line, what are you supposed to do? You are supposed to find the phase value. For example, this IF, it is, let us say, 0.6 amperes. Your VIL, let us say it is 120 volts, and your IIL is, let us consider, 4.2 amperes. These are just random numbers which we generally see in our laboratory. These are just random numbers. Treat them as random numbers, not so hard and fast rule, correct? Yes. So now what happens is, if you try to find the phase value, see this IF, it is already, it is DC, right? So no point, this is going to be 0.6 only. What about this one? This will become 120 by root 3, correct or not? Somewhere around 85 volts. And this is going to be line. Since we have considered star connection only, in star we know that line current is equal to phase current, so it is same, so it is going to be 4.2 amperes. This is just the example that we have taken, correct? Yes. So this is what is the data that you get after having ZPF test. Is it correct? Is it right, sir? Yes. So basically the test data that you get is your VIL versus what? VIL in phase value we need, versus IL, versus IF, IF when IL is rated, means whenever rated current flows, what is the voltage and what is the field current is what we are interested into. That is the only thing we need to understand. Okay, so this is what we get after having the ZPF test. And now let us discuss that what is the exact procedure through which we will be finding out the voltage regulation, because for us V full load is not important. Why? Because that will be already provided, that will be given, correct? What is important for us is the no load voltage, correct? EF. So now let us try to see what are the different methods through which we can try to find it. So let us see that. We all know that no load EMF, let us consider if EPH is equal to nothing but VPH plus IARA. Note all are phasor quantities, plus IAXL this time plus IAXAR. This is leakage drop, this is armature reaction drop. Leakage drop, this is armature reaction drop, correct? Yes, no problem, sir. So this is what we have. Now the way we are trying to do this, see, for us what is important? For us what is important? See here. What we will do, this is the complete formula for EPH, correct? Right, sir. So what we will do is we will bifurcate this formula into this much only. And for this calculation, for this part calculation, we will be using the formula which we had learnt in EMF method. So kind of we will be doing EMF method formula. EMF method formula we will be using, and let me call this particular voltage that we will get by adding these factors, let me call that voltage to be E1. So this is going to be our first step. How do we do that? We will come to it. Okay, no problem. Correct. Now once you have got this value of E1, what are you supposed to do? You are going to go to the OCC characteristics. You are going to go to the OCC characteristics and there find the value of field current for which this voltage is available. Means, for example, if this particular voltage is, let us consider 100 volts. So for that 100 volts, how much is the field current in the OCC characteristics is what is our point of interest. So let me call that particular field current to be IF1. Definitely you will understand this even more detailed way as soon as we start with the problems. Okay, yes, anyways, so this is the way. So you have got one value which is IF1. Now what we will do, this particular value, this IAXAR value, from this you will directly get IF2. You will directly get IF2 from this. You will add both of these values now. How do you get this? I will tell that, don't worry. You will add both of these values now. You will add both of these values now, and you will use MMF method equation for this. You will use MMF method formula. The formula that you had got in MMF method, you are going to use that. And once that is used, you will be getting EPH. So that is going to be the procedure. Now how to go into even more details about it, let us see next. Okay, yes. So step 1, what is our step 1? Step 1 is to find E1, correct? Yes. And E1 is equal to what, sir? EMF method. By EMF method we know it is V phase cos phi plus IARA the whole squared plus V phase sin phi plus or minus IAXL, correct? Now in this formula, in this particular formula, what do we have? We get, we know when plus has to be used and when minus is to be used. Plus is used for lagging here, plus is used for lagging condition, and minus is used for leading condition, correct or not? Whenever it is leading, minus is used. Whenever it is plus, lagging, correct? Yes, anyways, so now let us see how do we go about it. So in order to find even, what do we need to have? The first thing we need to have is the OCC characteristics. So let me have OCC characteristics like this. What is OCC characteristics, bacha, tell me? Yes, this is field current IF in amperes, and this is going to be VOC phase value, correct or not? Yes sir. Now you are having OCC characteristics somehow like this. We have already studied this, correct? OCC characteristics already we have studied. So and then it is going to get kind of saturated, correct? So this is OCC characteristics, we already know. Now what are you supposed to do now? See, you have to locate some point from the short circuit test. What is that point? See, you have to locate point number A. You have to locate point A from the short circuit test. From where? Short circuit test. What is that point A? Coordinates. The point A coordinates are nothing but IF and V. IF comma V. In the sense, see, it is a short circuit test, correct? Yes. And in short circuit test, you know voltage is 0. So let us put voltage to be equal to 0. And when that voltage is 0 and your rated current flows, correct? That is what we have the short circuit test for, right? Whenever rated flows, current flows, correct, at that time how much is the field current? So that field current, for example, if we consider to be 0.4 amperes, for example, if we consider 0.4 amperes, this is when my armature current IL, when my line current IL is going to be rated. At that time how much is the field current? Field current when my IL is going to be rated current, correct? Yes. So that particular value, for example, if it is 0.4, so let me have that value to be here somewhere, correct? So let me plot this point A. This is point A, simple. Let us consider this is 0.4, correct? Yes. Now the next point that you should have is what? Next point you should have is point K. Is point K, and this K point you will get from the ZPF test that you have just performed, correct? Yes. How do you get this particular ZPF test? Let us understand. So ZPF test values, what did you get about the values? You got these values, correct? You got what values? You got VIL versus IF, correct? Yes. So you basically got field current as well as VIL. So let us have that. So point K coordinates will be what? IF and what? VIL, correct? VIL phase value. Always remember, we need all the values in phase value, because even if you take one value to be line, everything will get wrong. Either you take everything in line or you take everything in phase, but don't do that one value is taken as line, other is taken as phase. No, that should not be done. Please remember this. Okay, anyways, so now this is what is a k point, correct? Let us consider this k point to be equal to, let us consider 0.6 comma 120, just for time being. This is just assumed values, no calculation has been done. These are just assumed values, okay? Yes. So let us see what happens now then. So this is a k point. So here if you have 0.4, then 0.6 will be somewhere ahead of this, correct? Yes. And at the same time, what is VIL phase? VIL phase you are considering 120. So let me consider here somewhere 100, 200, something like that. So above 100 somewhere you will get. So somewhere here you will be getting what? You will be getting the point. Okay, let us write one more time. Field current IF, correct? And this is what? This is your VOC, open circuit voltage phase value, correct? Yes. Your intention is to find even. So this was your OCC characteristics, right? Like this was your OCC characteristics. Now after that you used point A from the short circuit test. You got short circuit test, you got point A, and point A coordinates were what? IF comma V, which is what? How much is the voltage at this? That it is going to be 0, and IF We took it as 0.4 if you remember, correct? So somewhere here was our 0.4, so you had located point A, here was 0.4 amperes current. Now just against that you had got this 0.6 amperes to be here, correct, for point K. In order to find K, what did you do then? Yes, so point K was what? Point K was nothing but IF comma VIL, inductive load voltage, correct? So this IF we consider 0.6 which we got, and for example this is 120, so this is 0.6, and now to plot 120 here, for example if we consider 100, so above that we might consider 200, so just above 100 we will be getting here some point. So let me call this particular point also to be, so this is the point, this point is nothing but what? Point K, correct? Yes, this is point K. Now what are you supposed to do? You are going to draw, see, this is OCC characteristic, correct? You are going to draw the ZPF characteristics. You are going to draw the ZPF characteristics such that it goes parallel with the OCC characteristics. Such that it goes parallel with the OCC characteristics, kind of just as OCC characteristics are there, the same way my ZPF characteristics should also go, kind of parallel to the OCC characteristics if they should go. Now the next step and the most important step is to locate any arbitrary point P. Now we need to do only one thing, we need to locate one arbitrary point P. Arbitrarily locate point P. Some point P, some damn point P you please locate. So for example, if I locate the point P to be here somewhere, if I locate the point P here, now you need to have a segment PX. What? You need to have a segment PX. Now before that let me just write down, this is origin O, okay? You need to have a segment PX whose length is equal to segment OA. You need to have a segment PX whose length is equal to OA, means whatever is this value OA, similar way you should get this P. So let me have PX, so let me have it same length, let me draw, so this becomes PX, correct? Same as OA. PX length is what? Same as OA, sir, okay? Yes, no problem. Now the next thing is what? The next thing is we need to draw air gap line. What is air gap line? Air gap line is nothing but the tangent to this OCC curve. Tangent to this OCC curve is nothing but air gap line. This is what? Air gap line, or kind of tangent to OCC curve. Now what are you supposed to do? You are supposed to draw one line which is parallel from this X to the OCC curve. You are supposed to draw one line from the X to the OCC curve parallel to air gap line. So parallel to air gap line you are going to draw one line, and let me say call this point to be point S. This particular point to be, let us consider point S, okay? Yes sir. Now let me just join the triangle. So if I join the triangle, then this turns out to be what? This turns out to be your four-tier triangle. That's it, very simple, correct? This is nothing but your four-tier triangle. Now what I will do, I will drop a perpendicular from here. I will drop a perpendicular from here like this, okay? And this particular length, perpendicular length is nothing but the IAXL value that you need. The IAXL value, leakage drop value that you need is nothing but here, IAXL. Getting my point? IAXL value is nothing but this value. And whatever field current you required is nothing but here, which is IF2. Correct or not? Yes. Let me call this point here to be R. Or let us do one more thing. Rather than this, let me call this point to be point R and this point to be point S. No problem, no. Anyways, all are going to be any points only. They are just names, right? They are just simply names. You can take it any way you want. So for example, if I consider the point above to be R and the point below to be S, now I can say that the magnitude of RS, segment RS, nothing but gives you value of IAXL and it is in volts, correct? Because as it is, if you see, your y-axis indicates volts only. Similarly, PS, segment PS gives you the value of IF2 that you needed. Is it right? Yes. At starting we discuss you need IF2. So IF2 amperes also you will get. Now, what are we supposed to do here? Here, IF2 you have already got, correct? E1. What about E1? What is E1 formula? See, E1 formula is what? E1 formula. We need to get this value through EMF method, correct? Yes. EMF formula is what? V phase into cos of phi plus IARA the whole squared plus V phase into sin phi plus or minus IAXL the whole square, correct? Yes. Now in this particular equation, see, V phase is nothing but rated voltage already given in the problem. Then cos phi is nothing but the power factor already given. IARA, since value of IA is the rated current, RA is what? RA also you know, right? Resistance value already we have seen, given data, required data, right? RA, it is required, so this is also known. Similarly, V phase sin phi also we know. IAXL was unknown, but right now from the ZPF test we have got this value also. So kind of IAXL is also known now. So basically you have got this E1, correct? E1 value already we have got. You have already got E1 value. Now once you get this E1 value, once you get this E1 value, what are you supposed to do? You please go to y-axis, check for where is that E1. Kind of, if for example E1 is 100 volts, E1 is 100 volts, so you please try to see where is 100 volts. Then locate that E1 on your OCC, locate that E1 on your OCC, and from that OCC go to x-axis, from that OCC go to x-axis and then check for what is the field current at that particular value. Means what is the field current for E1 that you are supposed to find. So how do you find that? You please locate E1 on the y-axis, you please locate E1 on the y-axis, this axis, and then go to your OCC characteristics, and once you go to OCC characteristics, please check for what is the field current. That's it, correct? This is how the way you can deal with. Now next, see here, so this is your y-axis now, and this thing gives you IF1. Okay, now IF1 you know, IF2 also you know or not? Yes, IF2 you already know. IF2 is also given. IXL we just found, from that we got E1, and from that E1 you have now got IF1. Now once you have got IF1 and IF2, what you can use? You can definitely use MMF method. So by MMF method formula, by MMF method formula, what will you use? IF naught is nothing but equal to how much? Under root of IF1 the whole squared plus IF2 the whole squared plus 2 times IF1 into IF2 into cos of 180 minus 90 plus or minus 5. This equation we have already seen in MMF method. Is it correct? Yes sir, no problem. Now once you have got this value of IF naught, once you have got this value of IF0, what are you going to do? From this IF naught value, you please go to x-axis, because x-axis only has current. So x-axis, locate this value IF naught. From that IF naught, please go to OCC. From that OCC, please go to y-axis and then check what is the value, and that value is nothing but your EPH. So this is the story, correct? This is the story, very simple story. I will try to make a recall of it one more time, don't worry. And from this, once you have got EPH, then percentage regulation is what? Very simple. So EPH minus V phase upon V phase multiplied by 100. It is going to be your voltage regulation. We know that. Let us make a small recap of this particular ZPF method. See, what are you supposed to do? At starting, you should be having OCC curve. Please draw the OCC curve, correct? Yes, after drawing OCC curve, you please locate point A and point K. What is point A? Point A you get from short circuit test. In short circuit test, you get IF value and V value. What is voltage at short circuit? It is 0. What is the field current at short circuit? In the sense, whenever rated current flows, what is the field current? Whenever rated armature current flows, what is the field current? That field current is IF. So you please locate that point over here. After locating that point A, you are supposed to locate point K also. How do you locate K? For that K, you need to use the ZPF test data. What is that? It is nothing but IF into VIL, correct or not? So this is IF and VIL. So when you get IF and VIL, you will get the point K. IF and VIL, because purely inductive load we are considering, so that is the reason we call it as ZPF, correct? Zero power factor. Anyways, so this is our K point. Now once you get these 2 points, point A and point K, you please join them as if you are drawing something parallel to OCC curve. So as if you are drawing something parallel to OCC curve, you please join them like this. Now the moment you draw that parallel, then arbitrarily choose any point P anywhere. What did I say? Arbitrarily choose any point P anywhere. So for example, if you choose point P to be here, now the moment you choose point P to be here, then what will happen? Now you are supposed to take a segment PX. You are supposed to take a segment PX whose length is equal to OA. Whatever is the length of OA, the same length you are going to take for PNX. So PX, the same length is going to be there. Now next step is you need to have the triangle as well, correct? For that, you are supposed to draw a air gap line here, and you have to join this X point with the OCC curve in parallel to the air gap line. Means the way air gap line is there, at whatever angle it is there, the same angle your X point should also move towards the OCC. So when you are going to OCC, for at OCC you locate a point R, and now you please drop a perpendicular. Now this particular perpendicular which you drop, this particular length, this length is nothing but IXL. So you have got the value of IXL, correct or not? Yes. Now your EMF method thing, by using EMF method formula, you are going to get what? You are going to get the value of E1. For that, your IXL was earlier unknown, but now it is known. So you please find that, you will find value of E1. For that value of E1, how much is the field current? Is nothing but going to be IF1, correct? And IF1 is known. What about IF2? This particular PS, this PS is nothing but going to be IF2. It is your field current. So IF2 is also known. IF1 you have got now. Now you need to add IF1 and IF2. How do you do that? By using MMF method. So by using MMF method formula, you will be doing this, and then you will be using this particular formula, and then at the end you will be getting IF naught. And when you get IF naught, you please locate what is the voltage in OCC characteristics for this particular field current IF naught. And whatever is that voltage is nothing but your no load EMF EPH. So your regulation can be easily found out in this particular manner. I hope I was able to explain you this particular ZPF method in details. Thank you very much.